So, what are humans doing that is adding greenhouse gases to the atmosphere? Well, burning fossil fuels is the major answer. So, what we're going to do here is we're going to look at the chemistry of why burning fossil fuels adds carbon dioxide to the atmosphere. So, we're going to do that by using propane as an example fossil fuel. The chemical formula for propane is C3H8, and gasoline and diesel have similar formulas, but they're more complex. So I chose propane just because it's simpler and a little easier to work with. But you should notice that all of these fuels, they only have carbon and hydrogen making them up, which is where the name hydrocarbons comes from. So for propane, the C3H8, you can see in this image that I've got different chemical formulas, different ways of representing the chemistry of the molecules. So up here, this is the molecular formula model. So just writing the C3H8 is called the molecular formula. Down below it here is what we call a ball and stick model, and you can build these with styrofoam and toothpicks, that sort of thing, marshmallows, toothpicks, whatever, or draw them like this. Up in the upper right hand corner, we call this a space filling model, and you can see it's like the balloons have been blown up and sort of squished all together. And then finally, the fourth one here is called a structural formula model. So they all show the same thing, just in different methods. All right, we are going to use Legos. So if you're in the classroom, you're going to have the Lego set in front of you. If you're at home and don't have access to Legos, it's fine. You can just cut up pieces of paper and label them. So I've got the list here on this slide of what you're going to need. So I'm just going to talk through using Legos for now. So go ahead and build yourself the propane molecule as shown. So you should have 3 carbon Legos and 8 hydrogen Legos to make up this molecule. And what does it mean to burn? Burning chemically just means mixing with oxygen. So oxygen in the atmosphere, if you remember, comes in a diatomic molecule. So it's 2 oxygens stuck together. And you can see I've got the models there, the structural, the ball and stick, the space filling, and the molecular model, all showing those 2 oxygens stuck together. So let's build some oxygen, and with the Legos, we're going to use the red ones, and I'm going to ask you to build 5 oxygen molecules. So you're going to stick 5 pairs of oxygens together. And at this point, you need to close the lid of your Lego box, or whatever you're using, because we're not going to use or put away any. These are our molecules. So put the Lego box aside. And now we need to burn the propane. So what does that mean? Well, for the purpose of our model, what it means is breaking everything apart. So I know you just built it all. Now I'm asking you to take it all apart, all right? So disassemble all of the Legos into a pile in front of you. So one of the things that's made chemically when hydrocarbons are burned, propane in this example, is water, which is H2O. So take a look at the Legos you have in front of you and build as many water molecules as you can with your pieces, right? Don't go back into the box. So we're using white for the hydrogen and red for the oxygen. How many water molecules can you build? So here is an example of what those molecules should look like with Legos. So what happens now with what we have left over? So we've got blacks and reds, right? We've got some carbons and we've got some oxygens. And as you might have guessed, based on what we're talking about, carbon dioxide is what's going to be built. So here is an example of carbon dioxide molecules using the Legos, and you should have been able to build 3 of them. Burning propane produces water and carbon dioxide, and we know carbon dioxide is a greenhouse gas, and actually water is also a greenhouse gas. So these gases up in the atmosphere trap heat, and that is called the greenhouse effect. But let's look at the chemical formula of what this looks like. So I'm going to use the molecular models here, the C3H8, so propane plus 5 oxygen molecules, 5 O2s. So we're going to write the chemical formula. What happens when those two are burned? So we're going to start with these. What do we end up with? Well, we know that we ended up with water, right? So H2O. And we know that we ended up with carbon dioxide, so CO2. But the problem is that this formula is not balanced. So we were very careful to do this model with a single pile of our molecules, our atoms, right? We didn't add any, we didn't lose any. And right now what I've written doesn't make sense because the number of each of the molecules on each side of the arrow is not equal. So we need to go in and fix that. So, okay, here's what it looks like. And this is just a little intro. We're not doing a lot of chemistry here, but if you've never looked at chemical formulas before, let's look at it closely here. So, as I said, on each side of the arrow, you want to have the same number of atoms of each. So let's look at the carbon to start with. On the left of the arrow, we've got carbon only in the propane molecule, right? There's none in the oxygen molecule. So we've got 3 here. So on the left, we have 3 carbon atoms. So it should be true that we have 3 on the right of the arrow as well. And looking, there's none in the water, but we have 3 carbon dioxide molecules. So there are 3 carbons. So that balances. We're in good shape. How about H? So again, on the left, it's only in the propane, and there are 8 of them. And on the right, there's none in the carbon dioxide, it's just the water. We've got 4 water molecules, and each of them has 2 hydrogens in it. So if we have 4 molecules with 2 each, 4 times 2 equals 8, and we are balanced. That is an 8, really. Okay, oxygen. Again, there's only oxygen. There isn't oxygen in the propane, so we've got 5 diatomic oxygen molecules. So if there's 5 molecules with 2 each, that's 10. And on the right side, we've got oxygens in both of the molecules, so we're going to have to add them up here. So we've got 4 waters that have a single each. So there's 4 oxygens here. And then we've got 3 carbon dioxide molecules that have 2 each. So 3 times 2 is 6, plus our 4 over here is 10. And we're good. Our equation balances. Matter is conserved.